Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 46 on the subject of computer organization and assembly language programming. The title of today's session is Getting User Input via Read and Command Line Arguments. Well, this slide shows today's agenda. This was a long awaited topic, that is to write assembly programs that process the input given by the user via keyboard. And today we will discuss different ways of getting input from the keyboard via the system calls, library calls, as well as the command line arguments. And I will also show a demonstration of example x86-64 assembly programs that do all this job. Well, dear students, writing a computer program in any programming language, a programmer may need to get input from the user via keyboard and later display the result on the screen or std out. Almost all programming languages like C, C++, Java, Python, and so on provide different library functions that perform all this I/O functionality. Well, dear students, internally all these library functions make use of some operating system service to perform the task. And today we are going to discuss three different ways to get input from user via keyboard in x86-64 assembly language programming. And these are by making a system call during the execution of the program, by making a library call during the program execution again, and the third is using command line arguments before the program executes. Well, dear students, the input given by the user must be properly tested or validated to ensure that it is as per the expectation of the program. A malicious input can include codes, scripts, and commands which, if not validated correctly, can be used to exploit vulnerabilities like buffer overflow, cross-site scripting, SQL injection, and so on. Okay, so let us first start with getting input from user via keyboard using the famous read system call. My dear students, we have understood and used the write system call in almost all our programs so far. Let me quickly recap as to how we can make use of a system call in general. If we talk about x86-64 microprocessor running Linux operating system, we know that the system call ID needs to be placed inside the RAX register before we make the syscall instruction. The next step is to place the system call arguments, and the first 6 arguments are placed inside registers, namely RDI, RSI, RDX, RCX, R8, and R9. And in case of more than 6 arguments, we push them on the stack. And finally, after the system call returns, the return value can be found inside the RAX register. Well, dear friends, every operating system has its own set of system calls, and every system call has an associated ID. On my machine running Core i7, running Kali Linux 5.3, there are a total of 433 system calls. On your system, it may vary. Anyway, you can find the IDs of different system calls inside this file on Linux machines, unistd_64.h. And these are some of the important system calls with their associated IDs. Well, this is the C library wrapper of read system call, which is passed 3 arguments. The first argument is the file descriptor, from where to read. Since we want to read the keyboard, so we will place a 0 over here, because the 0 represents the standard input. The second argument is the address of the buffer, where the characters or bytes read from the keyboard will be written. And this third argument is the number or count of bytes read. So to sum up, the read system call attempts to read up to count bytes from file descriptor fd and place them into the buffer starting at address buff. And of course, it returns the number of bytes read. Okay, now let us see a program that prompts the user to input his or her name and display the uh, hello message. So this is the code. Let me describe this code to you. Well, dear students, these 5 lines of code display a message inside the string text1, what is your name, on standard output using the write system call, because we have placed a 1 inside RAX and 1 is the system call ID of write. And these 5 lines of code reads username inside the string name by first placing the read system call ID inside the RAX register and the 3 arguments inside RDI, RSI and RDX registers, and then it makes the sys call. So after these 5 lines of code executes, whatever characters user has given will be placed inside this name variable, which is declared inside the uninitialized data section having 10 bytes. Okay, so then we come up over here. This is used to display this string text2, which contains hello Mr. dot and a space. And finally, this again displays a string name in which we already have read the name of the user. So overall, this will display the message hello Mr. whatever name we have entered. And finally, the program makes the exit system call to terminate normally. And my dear students, this is how we can assemble, link and execute this program on a Linux terminal. I hope this code makes sense to you all. My dear students, please download this program from the course Bitbucket repository and run it at your own time. And I move ahead. Okay, so now let us repeat the same logic, that is getting username and displaying a hello message. But this time, let's use the C library functions instead of the system calls. And this is an example assembly program that is exact replica of the previous program, at least in logic, but it used the C library functions to do all the I/O. So we are using the famous printf library function to print characters on screen, the getus library function to read the keyboard, and the exit library function to terminate the program normally. Well, dear students, for simplicity and for learning purpose only, I am using this getas function. However, you must never use it as it provides no check for a buffer overrun. Okay, so let's move on to these 2 lines after this main function. This first line loads the effective address of format string 1, the starting address of this string, inside the RDI register, which is the register containing the first argument to this printf library call. So after doing this, we make a call to printf, so printf will simply print this string on the standard output. Do note this null character at the end of this format string 1. This is very much required. If you don't give it, this string will not be terminated once printed on screen. Okay, then over here, note that before calling the getS library function, we are placing its only argument inside the RDI register, which is the starting address of an uninitialized array of 10 bytes inside the BSS section, block storage start, uninitialized data section. And after reading the name from the keyboard, these 3 lines are displaying the hello Mr. Message followed by the name, using once again the printf call. And finally, these 2 lines make the exit library call, And note that we are placing the exit status 0 inside the RDI register before we make the call. So hopefully this program should work as expected. And to confirm, let's move on to our Linux terminal and give it a try. Let me show you the code first. Prog 2.nesum. So this is the same code, the two format strings. We are reserving 50 bytes over here inside the name. We are printing this string on screen. What is your name? Reading the name, printing the string as well as the name using the printf and exiting. Okay, so let me assemble this program. nesum-f-elf64. The name of the program is prog2.nesum. Let me link using the static option to GCC prog 2.o. Okay, so the linker being intelligent is giving us a warning not to use getAsLibrary function, as it will make our program suffer with the buffer overflow vulnerability. But for the time being, let's ignore it and run the program. ./a.out. Oops. So our segmentation fault. Okay, so let's load it inside GDB to find out the bug. gdb-qa.out. Fine, our PIDA, our program is loaded inside GDB with PIDA. You can note the prompt. Let me put a break at main and let me run. Great. So our program is running. Right now we are at the first instruction, which is loading this effective address over here. Let me press NI to move to next instruction without jumping or going inside the library codes. Fine, now I am on this call instruction. This instruction is going to call the printf function, and here is the problem. My dear students, I think I have discussed in our previous session that the stack pointer, that is the RSP register, where is RSP? Over here, it contains the address F68. So the stack pointer or the RSP, that is the top of the stack, must be aligned to a 16-byte boundary before making a call. Over here inside the code section, right now we are making the call to execute the printf function, and the address of the top of the stack right now is F68, whereas it should end with a 0 instead, at the least significant digit size. So the solution to this is either we push an 8-byte value on the stack so that it becomes 0, or we subtract 8 from RSP so that the stack is aligned before we make any library call. Let me quit this program. I have found the problem, and let's revisit our assembly program and correct it. Let me open it in Vim. So here is the code. So before making the library call over here, this is the call printf. Over here I need to either push some 8-byte data on the stack, or maybe I can just do a subtraction, subtract RSP comma 8, and to undo it, of course at the very end I may need to put an add instruction, RDI comma 8. So I have added these two instructions in my code. Before making the call, I have subtracted 8 from RSP to align the top of the stack, and over here I have added to undo that. And let me correct the spelling. So these are just the 2 lines of code that I have added. Let me Save and exit our program, clear the screen, and let me assemble it again, and let me link it, and let me execute it. So this time it is running and it is printing the string which we need to be displayed, and I want to enter my name and it works fine. For completeness, let me load this program inside GDB and show you what is the impact of adding those two instructions in our code. A.out, put a break at main, let me run. So once again we are at the same piece of code. The stack is not lined, you can see. Over here we have the subtract instruction now. Let me press NI. The stack is not aligned. We are subtracting 8 from RSP. Let me press NI. Now I am on this call instruction over here, calling printf function, and the top of the stack is aligned. You can note over here as well, the RSP register is 16 bytes aligned. The lowest hex digit contains 0. So that was the issue due to which our code didn't work previously and gave a segmentation fault. Okay, great. So let's fall back to slides. Okay, dear students, the last thing we need to do in today's session is getting the user input via command line arguments. Fine. Can anyone describe what do you mean by command line arguments? Oh, well, yes. A command line argument actually are the parameters applied to a program when it is invoked. And in many programming languages, these are the arguments passed to the main function. And in C and C++, the main function, which is the starting point of our code execution, can be passed two arguments. The first is of integer type containing the count of arguments, and this second is an array of type character pointer containing the space separated strings passed to the program. Well, dear students, this sample program, you might have seen this in your first programming course. This simply prints the command line arguments passed to the program on screen. Well, if we run this executable something like this, /my_xz learning is fun with Arif. So this is the expected output of this code. And this is the pictorial layout for your understanding. The first argument argc contains the count of the arguments passed 1, 2, 3, 4, 5 and 6. And this second argument argv, this argv sub 0 contains the name of the program. Argv sub 1 contains the first command line argument, that is learning, and so on to finally argv sub 5 contains this Arif. Great. And my dear students, if no arguments are passed, of course this argc will be 1, which right now is 6. Okay, at a very abstract level, this is how the arguments are placed on the function stack frame of the main function, just for your understanding. So if the concept of command line arguments are clear to you, this is where we use the command line arguments. Actually, the command line arguments allow a user to input data into a program without the program requiring a user interface. For example, this CAD program is given the file name via command line whose contents the user wants to be displayed on screen. And similarly over here, the user is passing the long listing option -l along with the directory name to this command ls so that it should display the long listing of the contents of this directory. Okay. So let us now discuss the logic of an x86-64 assembly program that receives command line arguments and display them on screen. Well, remember, when the control is passed to the main function by the underscore start C library function, the RDI register contains the count of the command line arguments, while the RSI register contains the address of the first argument, that is the program name, which we want to print. So let me describe this program step by step. So over here, you see before calling the PUTS library function, we are placing the address of arg v sub 0, that is the address of the first argument inside the RDI register. So remember, RDI contains the first argument which we need to pass to PUTS. And inside main, we have received the count of the command line arguments inside the RDI register and the address of the first string inside the RSI register. So we are placing uh, the address of the first string, that is arg v sub 0, inside RDI before we call PUTS. So once we call PUTS, the name of the program will be printed on screen. And after this, we are over here adding 8 to the RSI register so that it points to the address of arg v sub 1, that is the next argument. And after that, we are decrementing RDI, which contains the count of the command line arguments. And then we are performing a conditional jump if not 0 to main. We are actually, in this instruction, we are checking if the result is 0, then we exit the program by calling this ret instruction. And if the result is not 0, that is there are still the command line arguments to be printed, so we jump to this instruction over here. Well, dear students, it appears that this program will work, but it will not. And there are two reasons for this. The first reason is that this RDI and RSI, they are caller saved register, and this PUTS may overwrite them. So our logic will not work as expected. And the second reason that this program may crash is we have not taken care of the alignment of stack before making this PUTS library call. So the solution is we add these 3 lines of code shown in red. First of all, we are saving the contents of RDI and RSI register on the stack. And to align the stack before the call, we have subtracted 8 from RSP register. And of course, after this PUTS call returns, we need to restore the contents of these 3 registers. Dear students, do note that the sequence of these 3 instructions over here is reversed as compared to this. Okay. I hope now every line of this code makes sense to you. And let us once again move on to the Linux terminal and see a demonstration of this program. Let me clear screen, show you the program first, prog3.nesum. So this is the complete program, the same program which we have discussed on the slides. nesum-f elf64 prog3.nesum. Let me link it, gcc-static prog3.o, and let me execute it. Can anybody tell me how many command line arguments are being passed to this? 1, 2, 3, 4, 5, and 6. This Arif part is a single argument because given in double quotes. Great. So our code is working pretty fine. Let me show you another program, cat prog4.nesum. Okay. So this program actually receives exact uh, two command line arguments which should be integer values. It uses the a to I library function to convert them from ASCII to integer. It then adds them, adds the true number, and finally display the result on screen. So please go through the logic of this program at your own time. Let me assemble it. Nesum-f elf64. Okay, elf64 prog 4.nesum. Let us link prog 4.0 and let me execute it. Okay, it says you must enter two numbers. Let me execute it again. 54 and 32. So it displays the sum. Seems to be correct. Let me give minus 32. Great. It is working perfectly fine. Let's fall back to slides. Okay, so that is all for today's session. My dear students, I hope this session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.